Okay, before you start this video, I want you to stop and do the problems first without me. Okay, that's the whole point. See if you can do them without me, and then come back and watch this video and check your answers. Okay, and it's totally fine if you kind of like skip through the video and see like, oh, here's my answer number 9. Great, I got it right. And go on and on. Okay, you do not have to listen to all the explanation. Okay, just skip to where the answers are, and then if you got the wrong answer, then back up and watch it. Okay, do the problems first. All right, so I'm assuming you did that. So let's graph this thing. Our transformations, this -1 is going to take it right 1 and up 2, which means that instead of going through the point 0, 1, we're going to go right 1 and up 2. So this point will be on our graph. Instead of having a asymptote at 0, our asymptote is going to be up 2. So right here. And then the general shape is like this. And again, if you want to plug in points, you can. We're not going to be really picky about it, as long as you have that one good point. Domain is all real numbers. Your range is greater than 2, because we move that asymptote up. Oh, asymptote is 2. And our end behavior. At the right, it is approaching infinity. And to the left, it is approaching 2. Okay, and if you want to write approaching in there, you can. I just didn't really have space for it. All right, number 10. We want to have a function g of x that represents this function after a vertical stretch of 6 and a reflection across the x-axis. Well, we know to get it to reflect, we're going to need to multiply it by something that's negative. And to get it to stretch by 6, we need to multiply it by 6. If it was like flattened or compressed, then we'd have to have a fraction or something. So our function g of x is going to be this function, but we're going to multiply it by -6. That's it. If you'd like, you could check that on Desmos, but that's it, yeah. All right, so we have the function p of x equals 15,000, 1.06 to the x. It's modeling the number of students enrolled each year at a university. X equals 0 is the year 2010. So what does 15,000 represent in the function? Well, that's our a value out in front. So that is the number of students that we started with. And our starting point is the year 2010. At what rate is the enrollment increasing? Well, that's right here, because remember our normal formula is 1 plus r. So we've got the 1 right there. So r is 0.06, which is 6%. And the expected enrollment for 2020, well, we can just use our formula, 15,000 times 1.06. The year 2020 is 10 years after this, so we're going to plug in 10. You're going to do this in your calculator. You can plug it all in just the way it is. Your calculator knows order of operations. You should get 2,863. Round to the nearest person. It's just nice to do. All right, and our last one is we have a virus that's spreading through a network of computers. Each minute, 25% more computers are infected. Okay, so that's our R. That's 0.25. The virus began at only 1 computer, so our initial number is 1. You want to write an equation and then use the equation to find the number of computers infected after an hour. So A is 1. 1 plus our rate is 0.25. We're going to raise it to the t or to the x, whichever one you want to use. So our equation is going to be 1.25 to the t. Now, we want to use that to find the number of computers infected after 1 hour. Notice that this 25% growth happens each minute, so we can't plug in 1 hour. We need to be in minutes. So what we need to plug in is 60 minutes. So in this equation, we're going to do y equals 1.25 to the 60th. And when you do that, and we're going to round to the nearest computer, we get a lot of computers, 652,530. So after an hour, this is how many computers are infected. Hopefully those went well. If they didn't, we'll have time for questions tomorrow to make sure you understand what's going on with exponential growth.